Section 1.8 talks about complex numbers. Okay, how many of you have heard of complex numbers before? Raise your hand high. What makes complex numbers different? What do they have included in them? Say it again. An imaginary number. What do we use to denote the imaginary number? I. Very good. So that's what we're going to talk about in this section. We're going to talk about complex numbers. So let's start with a definition, okay? The imaginary unit is defined as I equals the square root of -1. This you're going to use regularly throughout this section. I is equal to the square root of -1. So make sure you remember it. Okay? I has the property that its square is -1. So in particular, I squared is equal to -1. So two things you've learned so far here. The imaginary unit, I, is equal to what? Square root of -1. Excellent. And whenever you have I squared, that's equal to? -1. I squared is equal to? -1. I is equal to? Square root of -1. Very good. Those things you'll have to remember whenever you're actually going through and simplifying problems here. Okay, that'll be helpful later. Another definition, which talks about principal square roots, or which is defining principal square roots. If a is a positive real number, then the square root of -a is equal to I times the square root of a, and the square root of a by itself is a positive real number. These are principal square roots. So an aside here, this is an aside, which means it's not necessary, but it's just extra. The square root of -a is equal to the square root of -1 times a, but we know the square root of -1, we know that's the square root of -1 times the square root of a, and the square root of -1 we know is? What's the square root of -1? I. Good. So this is I times the square root of a. That's how you get that. So a fact, using our properties of exponents here, if we take I times the square root of a and we square that, using our properties of exponents, we can rewrite this as I squared times the square root of a squared. This would, I squared is what? -1. And the square root of a squared is? Square root of a squared? Is it a? Yes, because the square root and the squared cancel to give us a. -1 times a is really just -a. Good. Okay? So those are some things. That's a fact. That's a fact. Okay? So let's go through an example. Example 1. We want to evaluate the following expressions. Is that too small? You want me to zoom in? That's good? Okay, we have the square root of -12. Our goal is to evaluate the expressions. So we have the square root of -12. That's equal to the square root of -1 times 12. 12, if we are trying to factor 12 into a perfect square times a number, is what times what? Is 6 a perfect square? But it is true. It's 6 times 2. But can you give me a way to factor 12 that it has a perfect square? 4 times 3. Good. So here, this is the same thing as the square root of -1 times 4 times 3. Why even write it that way? Because now we can write this as the square root of -1 times the square root of 4 times the square root of 3. Square root of -1 is I, yes? Square root of 4 is 2, but let's put that 2 up front so it'll look better. Okay? Are we all right to put it up front? Yes or no? Okay, so 2i times the square root of? Yes, that's it. That's it. What questions do you have?
How did we get 2i?
The square root of -1, we know by this definition is I. And then the square root of 4 is 2. And we just put the 2 out in front instead. Yes. Very good. So you could have written it this way first. And then rewrite it.
Why did we choose 4 and 3?
Can't hear you.
Why did we choose 4 and 3?
Talk louder.
Why did we choose 4 and 3?
Because you have a square root. Now, whenever you take the square root of a number, if you can factor the number underneath, the number underneath is called your radicand. If you can factor that as a perfect square times a number under a square root, then that means you can do some cancellation. You can simplify it further. That's why we use 4 and 3 instead of 2 and 6. Talk loud. Yes. For a square root. For the square root. You won't always be able to do it, but in this case we could. What other questions do you all have? Okay. Part B. We have -I squared times the square root of -64. What's -I times -I? Say it again. Positive I. So my question is, what is -I squared? It's -I times -I. I heard it was I. I heard it was -1. What is it? Say it again. Positive I. How are you all getting that? A negative times a negative is a positive, yes. I agree with that so far. I times I is?
I squared.
Oh, that's I squared, not I, yes? Well, I squared is what? -1. So this is -1. So -I quantity squared is what? -1. So here, this is equal to -1, so your side, times what? Times what? 8?
Because you, -8, you square root the 64, correct?
What happened to the square root of the -64? It's not just the square root of 64, it's the square root of -64. If you want it, go for it. I heard -8.
8i.
What are the steps? Your justification helps you along the way. What should you do first? The square root of -1 times 64, yes? And then rewrite that as what? So -1, which was the red one, times the square root of what? -1 times what? Times square root of 8 or square root of what? 64. So you have -1. What's the square root of -1? Say it loud. I. What's the square root of 64? 8. So what do we get when we multiply everything? Good, both of you. So you have to be careful. When you have the square root of a negative number, that automatically means you get an I pulled out because the square root of -1 is I. So you have to make sure you attach that to the square root of whatever that number was. Okay? What questions do you have? Okay, good. This is why I asked you to print out your notes. If you need to take a picture as well, if you need to. Definition. Yes. Definition. The powers of I. The powers of I follow a pattern that repeats with every fourth power. I to the first power is equal to I. I squared we know is -1. I cubed means we take I squared, which was -1, and multiply it by I. -1 times I gives us -I. And then I to the fourth means we take I cubed and we multiply it by I. That gives us -I squared. But I squared we know is what? -1. Negative times -1 is a +1. That's where that came from. So if we go back and I asked you to compute I to the 5th, it's going to be I. I to the 6th, -1. I to the 7th. Yes, and you're going to keep going. So you see what happens. All this does over here is just generalize that. So that says if you take your exponent, divide it by 4, and your remainder is 1, then you're just going to get I. If you take your exponent, divide it by 4, and you get a remainder of 2, it's -1, and so on. Remainder of 3 gives you, yes, a remainder of 0 gives you +1. Okay? So let's look at some examples that apply this. Okay? So we want to compute the following powers of I. We have I to the 15th. We learned this so we don't have to sit there and write I times itself 15 times. We can take 15 divided by what? 4. Good. We're going to take 15. We're going to divide it by 4. Our ultimate goal is to see what our remainder is. 4 goes into 15 how many times? 5? 5 times 4 is 20. 3?
Yes.
3? Yes. So 3 times 4 is 12. Good. 15 minus 12 is 3. Yes. So this is our remainder. So tell me which one are we going to fall into? This. Hey, very good. It's -I. Very good. We fall into this case where the remainder is 3. So we get -I. Go.
Where do we get 4 from when we do the I?
So where did the 4 come from here? So we know once we go past 4, this repeats.
Okay.
So that's why we divide the exponent by 4. Because after 4, it's just going to, it being the pattern, is just going to repeat. So that's why we divide the exponent by 4.
Thank you.
You're welcome. What other questions do you have? Okay, so we have to write our answer, right? So this has the form I raised to the 4n plus 3. So we get I raised to the 15 is equal to -I. Try B. You have I raised to the 132. Compute that. Compute I raised to the 132. I'll give you a minute. You can discuss it with your neighbors. Go for it. So we do 132 divided by 4. 4 doesn't go into 1, but 4 goes into 13. How many times? 3 times. 3 times 4 is 12. 13 minus 12 is? 13 minus 12 is? 1. Bring your 2 down. 4 goes into 12. How many? 3. Yes. 3 times 4 is? 12 minus 12 is? Hey, that is our remainder. Because 0 is our remainder, where do we fall? Here, 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 or here? 1, 2, 3, or 4? 1? 4?
No, we go back to 1 because you said after 4 it repeats.
We say what?
You said after 4 it repeats.
After the 4th power, the pattern repeats itself, which is correct. After the 4th power, the pattern for the powers of I repeat themselves. This means we have a remainder of what? 1, yes. Here we have a remainder of? Say what? Nothing. What's nothing mathematically? 0. Oh, 0. So this is technically a 4n plus 0, yes? That's what that technically is. So, do we fall into case 1, 2, 3, or 4? 4, yes. So what is this equal to? 1, yeah, good. So, this has the form I raised to the 4n. So, I raised to the 132 is equal to 1. What questions do you have? Okay. All right. So, some definitions. Let A and B be real numbers. The sum A plus BI is called a complex number. Formal definition. This is called a complex number. So this is the standard form. You got to know it. That's the standard form of a complex number. For A plus BI, A is called the real part. B is called the imaginary part. Some things to note. If B is equal to 0, then this complex number becomes A plus 0i. 0 times I is 0, so A plus 0 is A. So that means that when B is 0, you end up with a real number. If A is equal to 0, then A plus BI becomes 0 plus BI. That just gives you BI, which is a pure imaginary. That's a pure imaginary number. The collection, this is like a bold-faced C on paper. This is equal to, we talked about set notation before, so let me read it again. The collection C equals the set of all complex numbers, A plus BI. Remember what the bar means? Not absolute value. In set notation, this means such that. That means such that. A and B are real. So let me read it to you again. If you need to write it down, write it down. This means C is equal to the set of all, curly brackets, set of all elements, A plus BI. What's that? Such that A and B are real. Okay? This set is called the set of complex numbers. It's called the set of complex numbers. Okay? Now, with complex numbers, we can add them, subtract them, multiply, and divide them. You want me to write it out? You want me to write it out? Or are you good? Yes? The set of all complex numbers a plus bi such that a and b are real. Okay? That's how we interpret this, or how we translate that. Okay? So again, say what? Okay. So we can add, subtract, multiply, and divide complex numbers. That's what the rest of the section is about. Okay? How to do it. So let's go through some examples. You good here? Take pictures if you need to, I don't mind. We good? Okay, so some examples. Example 3, we want to simplify the following complex expressions. Remember, I squared is equal to -1. Here we are doing what to these complex numbers? Adding them, yes? So this is equal to, I'm going to drop the parentheses, -7 plus 4i plus 3 minus 8i. Then we're going to combine like terms. You got it. -7 plus 3 is -4. 4i minus 8i is negative what? Are we multiplying? -4i. Good. And that's in standard form. So we're making sure that our final answers are in standard form, a plus bi. So -4 minus 4i. Okay, good. Part B. What is our operation? What are we doing? Subtracting. Good. So can we just drop the parentheses? What do we have to do first? Distribute. Very good. So this becomes 4 minus I. Distribute the negative. Becomes what? Very good. Combine like terms. -I minus I is you're not multiplying. Negative, no. Negative what? Not -I. -2i. -2i, because you're saying you have a -1 minus 1, essentially, with i's attached, which gives you a -2i. Very good. So this should be -2i. And that's your final answer. 6 minus 2i. Now in C, you can do what? Multiply. Using what method here? I heard distribute. Foil method, yes, because you have a binomial times a binomial, yeah? So you multiply using the FOIL method. So here we're going to use the FOIL method. Remind me what FOIL means? Good. So, do you need me to write out before we simplify? Yes? Okay. So that's 5 times 2 plus 5 times negative 9i plus 2 times I plus I times what? Good. So now we simplify. We get 10 minus what? It's 5 times negative 9. Say what? It's 5 times negative 9? Negative 45. I just need you all to talk a little louder. It's hard to hear up here. Plus what? Minus 9i squared. Now we know I squared is what? Negative 1. So we're going to substitute that in. And negative 45i plus 2i is what? Good. Minus 9 times negative times I squared. I squared you told me was negative 1. So then we can simplify. That gives us 10 minus 43i. What's the rest? Plus 9. Good. So then combine like terms. What do we get? You got it. That's it. That's it. Okay? So we've added, subtracted, and multiplied. The only thing left is for us to divide. I'll record the rest for you, post the video. Okay? Remember to do your homework. I will also record 2.3, post the video for that. Remember, we'll take the first 20 minutes of class for you to ask questions about 2.3. If you have them, rest of the class next Tuesday will be for review. All right? Have a great and safe weekend. Thank you. All right. Now, given any complex number, a plus bi, the complex number a minus bi is called its complex conjugate. It's called its complex conjugate. And now that we know about complex conjugates, we can talk about the last operation to do with complex numbers, which is dividing them. Before we do, let's talk about this fact. 1. When you multiply a complex number, a plus bi, times its conjugate, a minus bi, because both are binomials, use the FOIL method. So when you multiply and expand, you get a squared minus abi plus abi minus b squared I squared. But remember that I squared is equal to negative 1, or no parentheses needed. It's just negative 1, right? So where you have b squared I squared, that becomes b squared times negative 1, but you already have a negative out here, so that changes to a positive. So that's equal to a squared plus b squared, which is just a real number. To simplify a quotient of complex numbers, we multiply the numerator and denominator of the fraction by the complex conjugate of the denominator. So quotient and fraction mean the same thing. So now we can talk about dividing complex numbers. So let's look at example 4. Simplify and put your final answer in standard form. Remember, standard form is a plus bi. Okay? Now, we have this quotient, or we have this fraction, 1 plus 2i over 1 minus 2i. So we have to multiply, it says, the numerator and the denominator of the fraction by the complex conjugate of the denominator. Well, our denominator is the 1 minus 2i. So we need to multiply both the numerator and the denominator by its complex conjugate, which is 1 plus 2i over 1 plus 2i. Then we rewrite this. This is 1 plus 2i, numerator times numerator, over denominator times denominator. So this gives us, using the FOIL method, remember you multiply your first, your outer, your inner, and your last. So we get 1 times 1, which is 1, plus 1 times 2i, which is 2i. Your inner is 2i times 1, so that's plus 2i, plus 4i squared. All of that divided by Since these are complex conjugates, we can use this fact up here. So we're just going to have a squared, which is 1, not erasing, which is 1 squared, so that's 1, plus b squared, so that's plus 2i squared. So now, because of room, I'm going to go up here, right? This is equal to 1 plus, we combine like terms to get 4i, plus 4 times negative 1, all over. A is 1 for us, so 1 plus b, which is, notice that for b, we're taking b, not the I. So b, which is 2 for us. So 1 plus 2 squared. So that gives us 1 plus 4i minus 4 over 1 plus 4. This simplifies to give us, notice that 1 minus 4 is negative 3. So negative 3 plus 4i all over 5. We want to write our final answer in this form. So that would be negative 3 over 5 plus 4 over 5i. That's our final answer. That's dividing complex numbers. Now, recall, 1, the square root of a times the square root of b is equal to the square root of a times b. And 2, the square root of a over the square root of b is equal to the square root of a over b. In order for this recall to be true, a and b must both be real numbers for this to be true. So as an example, our final example here, simplify 3 plus the square root of negative 2 quantity squared. Because we're squaring that quantity, we have to multiply the quantity times itself, as so. And then we use our FOIL method. So 3 times 3 gives us 9, plus 3 times the square root of negative 2 is 3 times the square root of negative 2. We'll handle that negative underneath the radical later. The inner is 3 times the square root of negative 2. And then the last is the square root of negative 2, quantity squared. So then we rewrite this. Remember, the square root of negative 1 is equal to I. So when we look at the square root of negative 2, that's the square root of negative 1 times the square root of 2. So that's I square root of 2, or the square root of 2 times I. Make sure that I is not underneath the radical. So this is 3i square root of 2 plus 3i square root of 2 plus, when you take the square of a square root, they cancel, leaving us with negative 2. So plus a negative 2. Simplify by combining like terms. So we have 9 plus 6i times the square root of 2 minus 2. So then 9 minus 2 is 7. So we get 7 plus 6i square root of 2. And that's your final answer. Okay, that's complex numbers. Do your homework.